Can we go? Okay, thank you so much. Welcome to this 40th, already 40th meetup of Paris WiMLDS. We are hosted by Datadog. Thank you very much, Datadog, for hosting us. And our first speaker, who represents the company, is going to tell you a couple of words about Datadog. But let's start with WiMLDS. And let's start with the first little poll. Who is here for the first time? Welcome to the community. Congratulations on this achievement. You came to the right place. Who is here for the second time? All right, we have quite a few people. And who is here for 3 and more times? Wow, we have pretty impressive, because you see quite a lot of people come here over and over. And so what is WiMLDS for those who have not been to our events before? It's an international organization, Women in Machine Learning and Data Science. We support and promote women and gender minorities who work in the field or studying in the field or are interested in the field. And we also have, it's an international organization. There are over 67,000 members worldwide, over 100 chapters. Chapter is just a word for branch or section, and over 30 countries. And so we have a code of conduct. The international organization has a code of conduct, which basically means we are inclusive, supportive, nice to each other, and don't criticize each other gratuitously. So we adhere to this code of conduct at our events. And maybe a couple of words about the Paris chapter. So it's founded in 2017, so already quite some time ago. And it's the 3rd largest in the world. So we are very proud of our achievements. There are over 4,000 members in our chapter. We have quite a large number of Twitter followers and LinkedIn followers. And it consists of currently a team of 4 people, sorry. So on the front, you can see Caroline and Chloé Agathe, who are 2 founders, so they cannot be unfortunately here today. That's me in the middle. My name is Natalie Chernetska, and I work in TerraLab, which is data infrastructure. And then at the back, you see Marie Saksik. So you can say hello to Marie, who is a senior data science engineer at Cybel Angel. Okay. And obviously, we also have a team of volunteers that help us with different tasks if need be. And also you can get, if you don't have yet, a t-shirt in different colors and different sizes, and you can wear it for jogging or for events or for other opportunities. Right, so what do we do? So I think that one thing important to point out, our speakers are always female, but as you see, all genders are all genders are welcome to attend our event. We both invite prominent speakers, like people who are already very well known in the field in Paris, also internationally. And also we are very much interested in finding out hidden gems, people who have not spoken in public yet, who might have only spoken in their team meetings. So think about it. Those girls who are sort of just starting your career, if you want to speak, maybe speaking with us is a very good opportunity. We also organize BBL. BBL is brown bag lunch. It's like you lunch and learn. And we organize on a regular basis to discuss research papers. Every Friday, if you follow us on Twitter, we share a paper written or co-written by a woman. And we also organize events with other groups because it's an international organization, also in France with other different organizations and on site. And something important I want to share immediately. So if you're interested in paper reading in a company of like-minded individuals, so the next session is 15th of December, lunchtime. We're going to announce it soon. And that's the name of the paper. So someone is going to present it and everyone else is welcome to read and comment. Okay, it's 15th of December. Now, if you want to connect with us, obviously you can also talk to me, to Marie. You can follow us on any social media. We are pretty inclusive and pretty friendly. We publish summaries of all our events on Medium, and we are very active on Twitter and on LinkedIn. Now, something very important. So as I said, this is international organization, and the newest chapter was launched in October in Ukraine. We are very much supporting Ukraine. We're supporting Ukraine in this barbaric war launched by Russia. And we already shared quite a lot of information on our social media. Also back in April, we organized an event featuring Ukrainian data scientist who was at the time living in Paris, although afterwards she had to leave. And we also shared quite a lot of resources, how you can support Ukrainian people, how you can donate, what you can do, what companies can do, what organizations can do. WiMLDS is not a political organization, but we believe that in times like this, it's our civic duty to support a country that is being aggressed. And so we are going to end this year with a bang. We are organizing a joint 3-country meetup on the 20th of December. It's going to be obviously online for obvious reasons. And we are going to organize it with WiMLDS Kiev and WiMLDS Poznań, our friends from Poland. And we're going to feature 3 Ukrainian speakers, 2 of them living in France. Yana Yatsun works at Banque de France, and Christina Grinko works for Google. And then we have another speaker who is entrepreneur in data science. So we're going to advertise this event. It's again going to be in English, and we are extremely happy to sort of welcome this new chapter and support it in any way we can in these extremely difficult times. Now, that's about us. And now about today's agenda. Fantastic agenda. We are very happy with about every speaker who is coming here. So we're going to have, first of all, Anne-Marie Tousch, who is representing our host, Datadog. Then Silvia Metelli, also a long friend of our meetup, talking about her research. And then Sophie Diakhate, fantastic topic about energy security and what is being done. And then we're going to obviously to have networking and cocktail. So our presentations and our meetup is normally in English, but obviously when you network, you can use whatever language you want. With this, let's start. If you tweet, you can tweet about this event using these hashtags. And I will cede the floor to Anne-Marie, who is going to present her research and her work. Please, Anne-Marie.
Thank you, Natalie. Okay, hi, welcome everyone to Datadog. My name is Anne-Marie. I'm a data scientist here at Datadog. And tonight I want to talk about machine learning readiness. More precisely, I want to try answering the question, how do you prepare for machine learning when you're not doing any? So yeah, it's a very, very wide topic. So I'm obviously only going to scratch the surface tonight. But hopefully this will be useful to you. First, a little bit of context. I'm working for Datadog. Datadog is a monitoring and security company. So basically we build products to make the life of developers better and easier to find faults in your systems. And yeah, if you want to know more, you can just come and talk with me after the talk later. Or you can visit our website. You can have a free trial if you want to give it a try. So yeah, pretty cool. We're building AI products for ourselves. A bit about myself. I started computer vision a bit at random in 2006 when no one was doing that. Maybe I was clueless, I don't know, maybe not. I've been doing computer vision at the beginning, but I switched a lot between more machine learning research and more software engineering positions. And more recently with Datadog, I'm doing more software engineering, trying to build the products in production. Still data science products, of course. So ML is cool. I probably don't need to deep dive into that. We can generate lots of things, images, can even have Copilot for when writing code now. So most probably when you're in the field, you have people coming to you and asking, hey, can I use machine learning? And tonight, I'll try to answer two questions. First, to help you talk with these people. Do you know what machine learning entails, really? And second, is it the right solution for your problem? I won't deep dive into that. That will be very quick. The next step will be, what can you do to prepare for machine learning? So that's what I was saying. How do you get ready to do machine learning when that's not what you're doing? So a few tips to get started. So what does that entail to do machine learning? What is machine learning really? Why is it so different from classical software? Classical software, very high level, you can say it's like an algorithm is like a function which takes an input and gives you some kind of output. And the developer will write the function, the algorithm. There's a lot of design ongoing. That's the high level idea. So for instance, you have a sort function, you take in as input an array, you give as an output the sorted array. If you want to design a chess AI, yeah, that's an AI. You want to devise an algorithm that takes as input chessboard positions and that takes as output a recommended move for the AI that's playing. So we've had algorithms for that for a long while, and it doesn't need machine learning. These functions can also make use of databases. You can get data from a big database to compute better outputs. It's still not machine learning. For instance, you can build a recommender system that would go fetch the books with the best ratings and recommend that to a user. It could filter based on some user preferences to find the best books. You may not, you can build a recommender system without machine learning. That would be very basic, but that would still work. So what's different with machine learning? The big difference is that in machine learning, the function is generated from an algorithm. So you feed the data to a training algorithm, which is written by some engineers, by a human, and you generate the function. And then the function processes the data as before. So for instance, for a chess AI, you'd use a database of games played and feed that into an algorithm and generate maybe some kind of neural networks, I mean the parameters of the neural networks from the data. And eventually you'll get the same kind of function as before. Based on the chessboard position, you generate the move. So that's the key difference, and that's actually not a small difference. The algorithmic part has been moved from just creating the function to it's the algorithm that generates the function, and the function is optimized based on the data. So the data takes much more importance. Okay, so what difference does it make in the end? It's still an algorithm. Let's take a step back and see what it means in production. When you put an algorithm in production, you usually just don't push the code like this. There's a whole ecosystem, a whole system around that, engineering, DevOps, to ensure that you have reliability, safety, that you can find the errors, failures in your system as fast as possible. You need to ensure that you're managing the resources correctly, etc. You need to build infrastructure, you need monitoring. We're a monitoring company, so we care about monitoring a lot. But essentially, you want to remove all risks from your system. When you start doing machine learning, and yeah, something which is important is that when you write code, the contract is clear because it's defined by a human person at some point, so it doesn't change too much. It can change with some configurations. Yeah, of course, there can be exceptions, but it's fairly stable. when you start using machine learning, the definition of the function depends on the data. So you can say you have some kind of weak contract. The function may change just because the data changed. And that changes a lot of things when you start to put that in production. First, you'll have much more components dealing with just processing the data. So there are new blocks here that are just about data processing. Yeah, by the way, this is inspired from the hidden technical paper. But the idea is that there are existing components from classical software that just grow a lot because you have usually more configuration, you need more resources, you need more infrastructure because you need the training, you have the serving of the machine learning models. You need to add more evaluation because you care even more about performance. And there are more failure points because the failure points is not only in the code, it can come also from the data or the feature extraction, which is related to code. So you can see there's quite a cost in putting machine learning in production. And one thing also is that due to the weak contract with data, ML, machine learning systems don't fail the same way as classical software. We're used to having stacked traces when there's an error in the code. That's not the case with machine learning. If the algorithm fails, it can be very subtle and can be very ridiculous, but that doesn't give you a stack trace and error. It doesn't, it fails silently. Whereas we could say classical software would fail loudly. It's like blinking, there are errors, stack traces. In the machine learning, that's not quite so. It might be even worse because if you get a better system, for instance, an image recognition system that becomes able to read labels, it can fail even worse in stupid ways. Like this one, taking the apple for an iPod just because of a label. So that makes, when you want to put that in production and you want to avoid failures, that's not really great. So that's another kind of cost that you have in machine learning. There's the investment in engineering per se, but there's also the risk of failure. So yeah, can I use ML? First, make sure that you know what that entails. You know there are costs, so that's the first step, know what that means. Then, okay, you can ask, is it the right solution for your problem? So I'll give you a few tips on questions that you can ask to help you decide that. And then we'll deep dive into how you can prepare for machine learning. So yeah, ML comes at a cost. We want to make sure that it's useful for our system. So the first question to ask is probably, do you need it? Are you reaching the limits of your current system? If your system is working fine in all the cases that you ever have, probably you don't need machine learning. So there might be several reasons why your system is not working in some edge cases, in some more and more often cases, maybe. Do you need to add rules, to add more code each time you get new cases? Is it becoming more and more complex to create new rules to handle the new cases? It might be also related to the fact that your data is growing, and sometimes a simple mathematical solution like a sort algorithm, which would work on a single machine, is not that easy to run when you have billions of data points distributed over a bunch of machines. So sometimes you just need a different solution. So if you answer yes to one of these questions, probably that's the right time to consider machine learning. Then there's another question you need to consider, which is what are the consequences of a wrong prediction? If the consequences are bad, well, you might still be able to use machine learning, but you'll need to have more safety nets after that. So yeah, let's say you're ready to use machine learning, you have a problem to solve with that. How do you prepare for the transition? Here I'm going to give you seven steps which I think are critical to a machine learning system. They may already be useful with a classical software system. You may already have them in your production system. The idea is that it becomes critical when you're doing machine learning. And the first is you need to quantify your performance. You need to have metrics that measure how good your output is. So in the case of a chess AI, for instance, that might be measuring how often the AI is winning, but that might not be the best metric for an AI because oftentimes you'll want to adapt that to the player, the level of the player. Don't want the AI to be too good so it wins all the time. It's not fun. So yeah, designing a metric is not obvious. For instance, if you're doing anomaly detection, what's an anomaly is often very much dependent on the context. So you'll want to have user feedback, but ideally what you want to do is not just say, okay, this is a good anomaly. You want to say, is it useful? Is it actually helping in solving issues? So what you want to reduce is really the time to detection or the time to diagnose the error. That's not easy to measure at all. So sometimes what you can measure is different than what you want to optimize. And what you can measure would be interactions with the application. Also, what you can measure online and what you can measure offline might be different. So you need to take care about that. The point is you probably will never have a perfect metric. You just need to know a metric is not perfect. You want to optimize what you have and iterate when necessary. The second step is to have a strong non-machine learning baseline. Very likely you already have it if you have something in production. So that can be a plain algorithm. For anomaly detection, we could even use a stupid threshold if we wanted. But there's not much to say here, except it's important to know what you have is a baseline. Third step, obviously, is that you need to start collecting data, and lots of data, as much as you can. You need to store it. You need to decide for how long you want to keep the data. And I'll advise you to use directly, as soon as possible, a data analysis friendly format and collect labels if possible. Why using a data analysis format? Because right away, the first step would be to start looking at your data, analyzing, cleaning it, making sure that you're actually collecting the right data, that you don't have missing data, outliers, and you can, as soon as possible, spot obvious patterns in your data, like seasonality, which would help you decide for how much data you want to store, for instance. The fifth step is now you have your offline data, you have a strong baseline, you can start running experiments. So it's time to try improving your baseline based on this offline data that you've collected. It's still not machine learning, but you can start measuring performance because you've also devised metrics. Step 6 is prepare for changes in production. So most engineering pipelines are designed so that it's easy to put in production new changes, new versions of the code, but it's not always that easy to measure the difference in performance because engineers oftentimes what they'll do are obvious improvements with clear contracts, or it's like technical improvements. So you can measure the improvements in latency or whatever. But here we're interested in more business-related metrics, which are harder to compute. So you need to think about how you're going to evaluate that in the production system. And finally, you'll want to test that as well. So you need to validate that this pipeline is correct, that the metrics that you're computing, you've been testing offline. So you design a new model offline, you tested it, it showed some improvements. So you've got your metric growing. You want to test that you have the same effect online when you test that in production. Hopefully, if it gave better results offline, you want it to have better results online also. You need to check that. It's not a given. And if that doesn't work, you might have to get back to your metrics. Why is it not a given? It might seem obvious. This is a very obvious example, but it might actually be trickier in real life. Let's say you've been training a system on cats and dogs and you give like a giraffe to it. It's not going to be able to tell anything, whether it's a cat or a dog. It doesn't mean anything. In real life, it will happen that you have new categories, new types of items arriving in your data, and you need to take that into account. So you need to be able to adapt your metrics for that, to adapt your offline data, etc. So yeah, if the metrics offline and online match, that's great. It's not the end of the game because it might still change over time, but it's a good start. If not, you'll have to get back to your metrics, data, etc., and make sure that you arrive to some agreements. Okay, so let's say this is all good. See, you've not started doing machine learning yet, but you're much more ready to start putting machine learning in production than before. So you can start thinking about the actual machine learning that you want to use. You can start thinking about reframing your problem as a machine learning problem. You can start playing with devising new features, so you'll grow your data pipeline a little bit more. So yeah, brace yourself. It's only the beginning. You're entering the world of MLOps. That's a big growing world. There's a lot of technologies. There's lots of pitfalls to avoid. But good news, you're not alone. There are a lot of people all trying to put machine learning in production. So welcome. It's only the beginning of the journey. So yeah, just remember, machine learning engineering is not exactly like software engineering, and you need to keep that in mind. It's hard to work with data. You need to think data, really. It's almost a paradigm shift. You need to think that data is what shapes your system. So you need clean, very clean data. Not using machine learning might actually be really fine. It's a lot about the process, about measuring things much more than having a fancy model. Sometimes you can have very strong baseline without even learning anything. Evaluation is key. So yeah, I keep thinking about metrics. You need to be evaluated to the cost performance trade-off, because when you put something in production, it has a cost. And if you don't know the performance of your system, you might be spending money for nothing. And yeah, the good news is that you can anticipate your machine learning future. You don't have to do machine learning actually to prepare. Here are a bunch of resources to get you started. So these are 3 books. Disclaimer, I didn't read them. And YouTube series with a Zoom camp if you want to get started. These are a few references I used to prepare that talk. So if you want to dig deeper, they're very interesting. Actually, the Leon Boutou's keynote at ICML is really great. I recommend watching it. And Software 2.0 blog post is also, yeah, it's pretty old already, but it's very interesting. And yeah, that's it. You may not have noticed, but a bunch of images were actually generated by an AI. Thanks for your attention. Do you have questions?
Thank you very much, Anne-Marie. I always admire your pedagogical approach and beautiful visuals, whether they're generated by you or by someone else. So I remember very vividly you gave the first talk at our meetup about data visualization. If you have not seen it, go and check the slides on our Medium site, and also obviously we are going to share the slides and publish a summary. But meanwhile, you have opportunity to ask questions to Anne-Marie.
So thank you very much. It was a really interesting talk. One problem that I have faced personally when deploying machine learning models is that there's an aspect you talked about, like having feedback on how your machine learning model is doing. And very often we run into the problem that we don't have enough feedback from the client. I'm wondering if you have faced that problem and like what is yours?
I do have the same problem. And yeah, it's tough. So one solution is try to get feedback from the customer. I'd say that would be ideal. But when you don't have a lot of data to show, it might not be that easy. The other thing is you have to hand label data. So you can't label thousands, millions of data points, actually, but then once you've labeled a little, you use proxies and you try to use maybe active learning, weak labeling. There are methods to generate labels, like weak labels from the data. So you have different levels of labels, strong labels, weak labels, and yeah. Basically try everything you can to get feedback. You just need that feedback, yeah.
Do we have any, please?
Actually, I'm working as a data scientist, so in the aerospace domain. So main issue I'm facing is some in case of multi-class classification and all, some categories having very less number of data. But so can we use this generative models for in case of a tabular data also? Because generative models I saw in computer vision and all, it's very widely people are using. But still now my client is giving sometimes the data they are giving, yeah, we are giving this much of data for each of the classes, but some minor classes will be the, so how we can tackle that problem? Upsampling, it's not working properly, that's why.
Yeah, I didn't talk about it. Again, I said it is a very wide topic. I'd say there are two different kinds of classes of problem. There are ones for which you can easily have a lot of data, like in advertising, you keep collecting data, you have huge databases, and your problem is what do you make with all that amount of data, because it's very big. And there are other classes of problems where your problem is that you don't have enough data. You have 100 data points at best, and even better if they are labeled, but you're not even sure. And it's really hard to collect data. And in that case, it's also hard to do machine learning. So my advice would be, okay, I'm sorry, I don't know about your specific system here. Generating images is easy because it's fitted with a lot of images, and it can be a chicken and egg problem, because if you're able to generate good data that's really similar to what your client has, well, you've almost solved your problem already, because it means you have you're able to make the distinction between true and false data. So yeah, I'm sorry, I don't really have a good solution here. You need to, it might be similar to the labeling problem, try to find similar data sets. Like for images, you can you train on some data and then fine tune your model on slightly different data. So you can try to find a data set that's slightly different but relevant to your problem, train on that. If there's more data, of course, that's interesting. And then try to fine tune with your data. So that really using transfer learning, basically. But yeah, that's not easy. We can chat more later on if you want.
Sure. Thank you.
I think there was a third question somewhere. All right, more than that. Let's start. But that will be fourth, will be the final. We have more.
Thank you for the speech. So in the presentation, I remember you mentioned about the cost and performance evaluation. Do you have any kind of like threshold to thinking that it's like worth a try? Like if it's more than 2 times of the cost, it's like worth a try, or do you have any like threshold about this to make like this decision, or it depends on the like management maybe?
Yeah, I'd say it depends how much you can make the decision as well. It really depends on your business, I'd say, how much you can invest in risking to put something in production that you might not trust as much as you can. Yeah, yeah, it's a question of judgment. It's your own judgment. To be honest, I don't think there's any rule you can have on that. Trust your judgment. Yeah.
Okay, and I think we have one more question.
Thank you for the insightful talk. So from an organizational point of view, so you're suggesting that in order to before starting doing machine learning, you need to put into place all of this infrastructure. But often when we are faced with this kind of problem, we need to show some numbers to be able to put in this kind of investment to start doing this. So this is another egg and chicken problem. So what is your suggestion to put something like this into place?
Yeah, thank you. That's a very good question. Ideally, investing in evaluating performance doesn't cost too much. I start with that and try showing that the current model is failing. I think the most important incentive to investing into improving the model is being able to show that the current model is not working as good as it should, and that's hurting business. So basically you want to show that it hurts the business, that your model is not, the current algorithm is failing so often. So it's really about the limits of the current system. And I suppose the best way to show that is to measure the performance.
Okay, well, thank you, Anne-Marie, very much for your talk. Thank you for answering the questions. If you have more questions to her, you will be able to ask them and talk to Anne-Marie during the networking cocktail. Let's give you a big round of applause. Thank you very much. And meanwhile, I will welcome and introduce our second speaker. And second speaker is Silvia Metelli. She is a Marie Skołodowska-Curie Fellow in one of the Paris universities. She'll tell more about her research. She has a truly international background, studied in Italy, then worked in the US, UK, and now France, right? And she's going to talk about anomaly detection. Silvia, please.
Yeah, so thank you very much for the introduction and the invitation here. So as she mentioned already, I'm fairly new to Paris, so I felt very welcomed by this community. So thanks again. And thanks also to Datadog for hosting the event tonight. So I'm Silvia and I'm a research fellow in statistics. My background is mainly in computer networks, but here in Paris, I also work in healthcare applications. But tonight, I'm just going to talk about anomaly detection for cybersecurity purposes. So in the next 20 minutes or so, I would like to talk about how we can use statistical modeling for cybersecurity purposes. And in particular, I will focus a bit more on something that I've been working on quite a lot, especially in previous years, which is about how we can model and predict new edges in a large computer network graph, where the ultimate goal is to make anomaly detection, so to detect attacks, for example. So I think the reason why cybersecurity is so important is quite self-evident to everyone, but we are seeing increasingly sophisticated cyber attacks. The example that I typically make, but there are many others, is the WannaCry 2017 ransomware attack that involved more than 300,000 computers in more than 150 countries. So you can imagine the scale, and in general, the global number of cyber incidents is really increasing. So unfortunately, Statista didn't update the data, so I don't have more recent figures, but you can imagine that the curve is for sure growing. And also, besides the disruptiveness and privacy issues of cyber attacks, we also need to consider the costs of the attack, because it has been estimated that the average cost of just one single data breach is around $3 million. And this tends to be much higher for healthcare industry, for example, that I think it reaches almost $10 million. So of course, this poses a lot of questions also from a government point of view and policy making. So this, of course, well motivates the need to build and do more research into constructing intrusion detection or anomaly detection systems to monitor large enterprise computer networks looking for attacks or anomalies in general. But unfortunately, computer networks tend to be very complicated because they have a very complicated structure and the size, of course, of the network is very large. So some of the main challenges that we face when we want to build this intrusion detection system is how to deal with computational speed and scalability. Because ideally, we would like to build a method that is able to do detection in real time. That's the final ultimate goal, not always possible. So before going into more the methods and the anomaly detection methods, I would like to just show a little bit the data that we are dealing with and the size of the data that we are dealing with. So of course, there are many different, and there is a variety of computer network data. Maybe the most two typical ones are NetFlow data and authentication data. So in NetFlow data, we just monitor, we have collection of traffic between one IP address and another IP address, and also typically time, duration of the connection, the port that was used, the protocol, the number of bytes transferred, and so on. So the data are very rich. Another type of data, maybe most often I've seen that is authentication data, which is a little bit simpler. So we just have a timestamp with a user and the computer between which the authentication event happened, and also whether the authentication was successful or not. In terms of data sources, of course, that depends a lot on the availability of the enterprise to share this data. Sharing this data is very rare. The data that I've always worked with, and also that I will show talk tonight, come from Los Alamos National Laboratory, which is intense research intense national laboratory in the US, which is very famous also for, of course, for security science. And in this case, I will use authentication data, where we have data for 58 days of contiguous traffic, where we have 1 second resolution. So the data size is really large. And just to let you have an idea, this is how the network looks like just in the first day, in the first 10 minutes of traffic. And just remember that we have 58 days of traffic, 24 hours each day, 1 second resolution. So you can imagine how the size of the final full network is. Not possible to plot it. So just to say a bit more about the network, of course, this is a snapshot of the network at minute 10, but the network evolves over time. So it is a dynamic network, of course. And from a mathematical perspective, we will encode this network as a graph, actually as a time series of evolving graphs, where each graph is denoted by a set of nodes or vertices, so the little dots that you see, and a set of edges, so the connections between each of these nodes. In this case, the nodes are the users and the computers, and the edges are the connections or the authentication events between the two. Okay, so as I was saying before, the final goal here is to do anomaly detection, or better, intrusion detection. So what we really would like to see is to detect, for example, an intruder which is traversing through the network. So just as we look at this really simple toy example, we have this intruder that is traversing through the network, and at the beginning it starts getting a foothold through the network, and then it gains more and more way, and it just spreads a little bit like a virus through the network, compromising more and more nodes. So far in the literature, let's say, there are two main ways in which we can do anomaly detection. The first one, which is the typical one, is called signature-based anomaly detection. It is a very effective and efficient method because basically you screen the network comparing the attack to known violations. So violations that have already happened. So this is very efficient in terms of computational cost, but the problem is that you will not be able to detect an attack that is not present in this database of attacks. And we know that now it's really, really easy for an intruder to come up with a slightly different or novel attack. So we need more effective methods. So the other approach, the alternative, is to go for what we call anomaly-based methods, which are based on the following rationale. So first, we need to build a model that should reflect the normal evolution of the system under the assumption that there are no attacks. And then we look at anomalies as possible and significant deviations, so from a statistical perspective, p-value, from the normal behavior of the network. So in this case, we are also able to detect novel that we call day zero attacks. But of course, it is clear that for this method to be effective, it is really important to have reliable models for the normal state of the evolution of the network. And for us here, since we restrict our attention on the topic of new edges, this will mean having a reliable model for the evolution of the new edges in the network. So just to say a bit more about what new edges are, new edges are connections between a client and a server that were not previously observed. So again, if we look at a toy example of the evolution of the network, we have a set of clients and a set of servers, and at some point, a client will connect to some servers that he has never connected to before. So this is a new edge. And the reason why we think new edges can be important in this context is because they can be signal of anomaly. Because an intruder that is new to the network and is trying to traverse will necessarily make new edges. But also, on the other hand, new edges can be completely legitimate because clients can just start establishing new connections. So not necessarily this will mean that we are, if we see a lot of new edges, that we are seeing an attack. So it is very hard to properly model new edges. And in particular, we need to distinguish two different components. First, we need to understand the rate of occurrence of the new edges, but also we need to predict, and this is more challenging, the identity of the new edges. And we claimed, at least in this work, that to identify the identity of new edges, we need also to understand a bit more the latent structure of the network. So we know that these networks tend to have a quite clear latent or clustered structure where similar clients or servers tend to be clustered together. And this can help us in identifying the new edges. So why we think this latent structure is so important is because we think that similar clients tend to connect to similar servers. So what can be very unusual for a host, not necessarily is unusual for another, because that depends a lot on their typical behavior. So if you're able to detect this latent structure, this can also be predictive of similar future interactions. So it is really important to build a model that is analyzing new edges, also taking into account this latent structure. And when I say latent structure, it's a more general word to say cluster structure. Okay, so this is the model that we proposed for analyzing new edges. The model is, everything is time varying, of course, because we are analyzing time varying dynamic network. So the main point of this model here is to distinguish this first part here, this rate, from the second part here. So the first part relates to a seasonal, let's say, baseline behavior, because we know that this kind of networks tend to have seasonal behavior. For example, at some, not necessarily the traffic is the same at night or at weekends, so there is a sinusoidal pattern. And then also, of course, we need to come up with predictors. of the probability of observing a new edge. So here we use a few, but of course there are many others that we can include in the model. So we construct some measures of what we call time varying in degree of the node and out degree of the node for a client and out degree of the node for a server, which means the number of connections that a client receives and the number of connections that are emanating out of a server. And also some, let's say, an indicator of new edge burstiness, because when we are seeing an attack, it is typical to see a burst of new edges occurring all at once. And then to take into account this, this latent structure, this cluster structure that I was talking about before, we construct what we call a matrix of attraction between a client and the server, which should account for a similarity between them. We have two different formulations for this matrix of attraction. First, we model this using cluster membership indicators, and then also more flexible dot products of latent feature positions. I will not go much into the details of this, but I will just say a few words to make a distinguishment between these two formulations. And then again, in the interest of time, I will not say much about the estimation, but everything is embedded in a Bayesian framework. So we will use both what we call the likelihood of the model with some prior information to construct our posterior inference that will be that is carried out through typical simulation methods, so MCMC methods. So just to say a bit more about this clustering issue. So first, we decided to cluster the clients and servers in a quite strict manner, let's say. So our purpose was to bicluster together clients and servers, but this meant also to have let's say a finite representation of this clustering. So each data point was strictly allowed to belong only to one cluster. So for example, overlapping clusters were not possible. So we wanted then to increase the flexibility of this model, and so we changed this clustering configuration, and we used something that is based on a stochastic process called Indian Buffet process. We can go into the details of this later if you're interested, but it's I'm not going to go into the details here. But the important thing to say is just that this formulation is very, very flexible, and potentially it allows for an infinite number of latent features for each client and for each server when constructing the similarity between them. So the flexibility of the model is increased a lot. Okay, so this was it in terms of the methodological framework that we used. And so it's now time to see what happened when we actually fit this model to real data. So as I mentioned very quickly before, the data that we use come from Los Alamos National Laboratory, where we had both a bulk of data consisting of these 25 days of traffic and including more than 16,000 clients and 15,000 servers, but also very interestingly, we had some collection of red team activity, which means that during the period of data collection, a penetration testing operation occurred. And so some events and some clients were labeled as compromised. So we had labeled data, which is very good. So that made like perfect framework to test our methods. And in this figure here, you can see the rate of occurrence of the new edges, since we are concerned with new edges here. And you see that, I mean, the peak, the frequency is very high in the first day. But this is completely normal, because this is the time in which the clients will start establishing their traffic. And this will become, with time, the regular traffic. So of course, the rate decreases, but still will be far from zero. While for the red team, actually here we have a different scale. So this is much a smaller number of events. We have just a few events, so it's very hard to detect it. And just a few words more on the red team. As I was saying, we have 4 known compromised clients, but actually there's just one client, which is the first one, which is responsible for most of the activity, which happens here in week 2. The other clients connect to a very limited number of servers, and this makes it even more difficult to detect them. Okay, so of course, we tested our model, and we wanted also to compare if there was any benefit using the 2 different clustering formulations that I have briefly introduced. Overall, we saw that for all the model coefficients that we had, they were positive and significative. And so this hints at least at the idea that there should be an impact of introducing those predictors into the model, and also of the clustering structure. So actually the clustering part was the one responsible for the strongest impact. So it seems very, very important to introduce some clustering information into the model to help the predictive performance. And then, of course, we wanted, as I said, to compare the 2 formulations to see if there was any benefit of it. And we could see that in terms of goodness of fit of the model, that's the model under the more flexible latent structure outperformed the other one, although that came at the cost of a slightly higher computational costs. So this latent feature formulation is let's say the model that we use to perform anomaly detection. So if you remember at the beginning, I said that the anomaly-based method, it's all built on the idea to first model the normal behavior of the network and then look for anomalies. So we have reached this stage here. So let's say that we are happy with our latent feature model, and at this point, we need to perform anomaly detection. And anomaly detection in this case is framed in a sort of hypothesis testing framework. So the null hypothesis is that there's a normal behavior. Of course, this again happens over time. And then also we want to see if there is any departure from this model of normality learned. So the way we do it is to use a specific feature which is called posterior predictive p-values, which is a measure very frequent in Bayesian inference, but you can see it as a sort of p-value. So still it measures how surprising it is to see this new connection. So based on that, of course, we would have a sequence of these p-values over time, and for each authentication event, then we would need to combine them into a single score for each client. Again, I'm not going through the details here. I've completely skipped that step in the interest of time, of course. But what we end up having is a sort of a control chart over time for each client. And here I'm reporting the control charts for 2 out of the 4 infected clients. And as you can see, the p-values go well below the threshold, these red thresholds, which are the thresholds of anomalies. And so we are able to detect them, those infected clients. And just as a reference here on the right-hand side, you have an uninfected host. And you can see that his normal behavior always stays well above the threshold of anomaly. We were not able to detect the other 2 clients, but they were also making really, really low number of connections. So it was really hard to detect them. Of course, then finally, we also wanted to assess the accuracy of our anomaly detection framework. And this is typically done with something called ROC curves, where you can control for the a rate of false positive and true positive detections. So as we can see here, we're doing pretty well in terms of false positive rates. We have quite low rate of false positives, but there's still a number of true positives that we would like to detect. And on the right-hand side is just in log scale to see the differences a bit more. So just in conclusion, we have proposed this method, which is the Bayesian method and anomaly detection framework to model the rate and the identity of the new edges, because we claim that new edges can be very important in looking for anomalies, and also simultaneously detect any possible latent structure, so perhaps clusters that can aid the prediction of new edges. And from the application to computer network data, we had a relatively good prediction performance, and the anomaly detection also was carried out with good false positive rates. And we were able to detect two known compromised clients. Of course, there's a lot of room for improvement and many different directions in which a computer network can be analyzed. Here, we just focused on the topic of new edges. And just before concluding, let me say a few words about, in general, statistical research in cybersecurity. So this is a very niche topic. Like, there are really not a lot of groups in the world, at least from a statistical perspective, doing this. One of these, and maybe very active group, is back at Imperial College London in the Department of Mathematics, where I was part of, and most of this work has been conducted there. And the group is led by Nick Hurd, who was also my PhD supervisor, and Niall Adams, but also more recently, many others. So if you're interested into the topic, please make sure you check their work. It's great work. And also what I want to say is that if any of you are interested in performing some anomaly detection in computer networks, Los Alamos data are public, which is very, very rare. So they were not public before, but they are now, and these are the link. There are also different sources of data, authentication events, unified hosts, and more. So that's a great source of public data. And with this, I would like to thank you all very much.
Thank you so much, Silvia. It was completely fascinating. It was like mathematics, statistics, detective story. I mean, if I could go tomorrow to London and join this group. This looks fantastic. So please, you can seize the opportunity and ask your questions. All right.
How would you like, if you detected this, or this is, if it's like in production, whatever, what would you do? Could you like shut it down like automatically, or?
Yeah, that's a great question. So the main problem here is that, as I said at the beginning, ideally what we want is to have a real-time detection. So all of this framework is possible to be translated into a real-time detection because of the way the continuous time that we use to construct the model. But so far for us was an exercise to see if we were able to detect the compromised clients. This has not been deployed in real time in a system. But yes, in principle, what you want to do is to come up with the early warning system. So to be able to raise a flag very early in time before, if we are here, you want to raise a flag, let's say here, so quite early in time before most of the hosts will be compromised.
Any other questions? Sure.
So for now, how long does it take to catch this like anomaly behavior from the beginning?
So you mean how long did it take us to build the model, or in terms of
performance? How long does it take to catch this like abnormal behavior?
So again, this is not in real time. So we were just running the model, let's say in batch, and see at the end if we were able to detect them. The model, so the size of the data, as you've seen, is huge. So we had a lot of issues in terms of computational efficiency. We were also using very powerful servers, and where possible, we were parallelizing everything, but not always was possible due to the way that the model was constructed. But these are not, so I mean, it's models that will take you time to run. It's not something you can have a response quickly in time. So you'd need first to train the model. So in order to make it real time, you would need first to train the model in batch, and then once the model is trained, to do it really real time. But we were more concerned with the first phase, so to come up with the good training model, and to run that is not it's for sure it has large computational costs, so it can take weeks. Just to give you a frame.
Any other question? Oh, yes, sure. Oh, two.
I'm not talking, just a disclaimer, I'm not an expert in any of these fields, this one. Maybe my question doesn't make sense, but have you considered to applying this model to other types of data? And I'm thinking here about like other kind of infection, such as epidemics.
Such as what, sorry?
Epidemics.
Okay,
right.
yeah. So I've never applied it to. So I actually I'm now working more in the field of healthcare. So more recently, since I came here to Paris, and part of what I'm doing is to precisely what you were suggesting. So to kind of use some of these ideas into completely different frameworks. So we have still high frequency data, for example, coming from patients monitored in ICU or wearable devices, where you have really continuous streams of data. And of course, the context is very different. But for example, if you think of monitoring vital signs like heart rate, looking for arrhythmia or something like this, this is something we are doing. I've never used it in the context of disease spreading or this kind of network, if that's what you had in mind. But yes, definitely, this is something that can be done.
Thank you once again, Silvia. Thank you so much. Let's give her a big round of applause. You also can continue asking her questions during the networking, but unfortunately the time is running and we would not want to miss our third speaker, who is coming to talk about something somewhat different. As you know, as you have noticed, winter is coming and we're going to talk about energy security. And so our speaker is Sophie Diakhate, and she's electric engineer and consultant in energy and securities at a company called Yélé. Let's see how we connect the computer. It should be working. Just a second. All right. Okay, Sophie, the floor is yours.
Thank you very much for this invitation. Clearly, I'm less fluent in English than the previous speakers, so please be gentle to me. I'm Sophie Diakhate, and I'm an energy consultant at Yélé Consulting for 4 years now. And I'm here to talk about the emergency of the emergency plan for the security of this winter. We hear a lot about problems on energy supply, and in fact, French electricity production will be in deficit this year because of many reasons. But the three mains are these followings. First, we will have a problem of availability of the nuclear fleet, because nearly half of them are nowadays shut down for many reasons, for maintenance, for energy policy, for ecological reasons, and so on. The second one is the risk of, on the continuity of the gas supply by Russia because of the war and because of the, how can I say, because of the sanctions of European Union. And finally, on the functioning of the European market, electricity market. And before we had in solidarity between neighbors that on what we could not count on for the next, for this winter. If we, to better understand these reasons, we need to understand the French energy mix. And if you have a look at it, we can see that the main product is the nuclear sources. After comes hydraulics and renewable energies like solar and wind. And after comes the fossil energies. And this inequality on the installation is reflected on the production. More than the half is produced by nuclear, and some little parts for the rest. What is important here, what we must remember is that if we have any problem on the availability of the nuclear, it will impact on the security of applying. So, as the transmission system operator, RTE is responsible of the security of applying and responsible also of the supply-demand balance. So, in collaboration with some stakeholders and with some authorities, it is implementing a plan consisting on reducing the as much as possible the risk of shutting down consumers. So the first step of this plan, the slide is in French, but I hope you understand, everybody. Okay. The first step was to understand the problem, to have solutions. What is clear is that we don't have ability to act on the production, only on consumption. So we collected data from the distribution transmitter operator in this, and we have an analysis of them that allow us to understand the habits of consuming. So we have in red on the streets, residential in blue, and green for the tertiary. And another point is that thanks to this analysis, we can notice that the peak is between 8 a.m. and 1 p.m. and between 8 p.m. and 6 p.m. and 8 p.m. And thanks to this, we can see that in the part in red is already doing his best. So the only parts where we can act is in residential and in tertiary. So after this this analysis, we find 3 types of actions. The first one is to consume better to reduce our consumption. It can be a simple act like switching off the light when you leave a room. Consume at the best time to smooth the peak of the morning and of the afternoon. It can we can do it by shifting some activities like the laundry. And the last solution is to do an additional effort when we have tensions on the electricity system. So to do that, we need to know when to act. And for that, we RT have created EcoWatt. EcoWatt is like the reader of the electricity reader. We have 3 colors: green, orange, and red. When it's green, we can do whatever we want. When it's orange, we have to pay attention because there are some tensions on the grid. And when it's red, we really need to do some effort to reduce the risk of shutting down. And we can find the information on the website, and there's also an mobile application that we can upload on cell phones. We can register for an SMS alert when it's a problem, and the societies that have specific tools can connect to the API. Here are some examples of levers we can do to reduce our consumption. I'm not going to do them in details, but we can act on the heating by reducing the temperature. We can act, like I said, on the laundries, on some activities. We can also act on as a device, depending on what we have at home. These actions will have an impact on the model of consumption, and we can have between 5 to 7% of consumption reduction if we all play the game and make efforts. It will help to avoid cutting down some consumers. As I said, the first step of the project was to understand the problem, to find the appropriate solution. And what helped us was data analysis. As I said, we collected them from this, and thanks to this analysis, we were able to have a more or less precise diagnostic. We were able to build the model of consumption, and we have not finished yet with it. In few days, we will start collecting data from, we have what we call EcoWatt partners, and they are committed to give us their data so we can collect them, use them to analyze their consumption and see the impact of eco acts on their load chart. Voilà. Thank you very much.
Thank you very much, Sophie. It was very enlightening. You know, these topics are everywhere, but it's very interesting to see actually what is the energy mix and what the data says and what are the simple things we all can do. So I open the floor to the questions. Sure.
Hello, thank you for the presentation. I was just wondering, when you presented the seasonality within the day, did you notice a seasonality within the week, like with people going to work, if the weekend the hours change or something like that?
Look at
is the weekend really different from the other days of the week?
Yes, because we. If we take the graph, we can see that all the part in green is in a tertiary sector, and then if we are in at the weekend, for example, all of the consumption on the offices and the best part of the tertiary doesn't work. So we don't have the same. We always have this kind of peak, but it's not the same value. Did I respond to?
Okay. Other questions? Sure. I'll start with you.
And so are you maybe monitoring this data quite closely recently? For example, do you observe like peaks connected to the football World Cup or stuff like that?
We don't have collected yet the data, but it's an important question. I think that we can analyze it to see if many people have watched the matches or not. But we don't have yet the data. I have to precise that the data we collect for the equal partners are not the residential data, because I say we, but RTE don't have the right to collect your data without your consumption.
Yes, I have a question about how confident are you for the winter? Since you've worked in this, and do you think EcoWatt will be followed? And yeah.
Honestly,
maybe it was
I'm
a bit
not
difficult.
confident. But if we all make efforts, I think that we can limit the consequences. But I don't think that we will have 100% of production. No.
Any other questions? If not, thank you very much, Sophie. It was really very good reminder what's like ahead. And obviously you can talk about these topics and other work Sophie is doing at Yélé during the cocktail. So that's it. We had 3 fantastic speakers, Anne-Marie, Sylvia, and Sophie. You have an opportunity to network. We would like to thank our host, Datadog, once again. And I would like all the speakers to come here and we'll take a little pictures, but all the rest you can start roaming and talking to each other. Thank you for being here.